Hello everyone. In the previous session, we have looked at implementing the linear regression model using PyTorch. All what we have tried to do is to find the right model parameter values, that is W and B. So the right values of W and B are found by the optimization process. So we have made use of gradient descent algorithm in order to come up with these right optimal values for W and B where we observe the minimal loss. So in this particular diagram that you are currently observing, I only have one single parameter for simplicity. In order to understand it graphically better, I only considered one single model parameter that's existing, which is weight W. And the cost function or loss function is being expressed only in terms of W here. Okay. So which typically is summation of y equal to 1 to n, yi minus yi hat whole square divided by n, which is nothing but MSE formula here. So the initial random value for weight is chosen and we calculate the gradient at this particular point, and then we try to find the updated weight by this particular parameter update equation, which is w minus eta times derivative of loss with respect to that parameter w here. So we update the weight and we move our weight to the next updated weight value. We compute the gradient again and the process is iterative. We just keep on updating the weights till we observe particular W value where we are observing minimal loss here. So this is one such value of W where we are observing a minimum MSC value here. Okay. So this is the overall perspective that we have gained about the gradient descent algorithm and which we have implemented in PyTorch as well. But if you are considering multiple parameters, like for a simple linear equation, it will be Wx plus B. So your yi hat is going to be Wx plus B, where we have two different parameters that are involved. And if you come up with this particular diagram, on x-axis you might be having W, on y-axis you might be having B. On z-axis, which I'm not representing now, it's nothing but your loss function, which is expressed in terms of both W and B here. So when you project your 3D diagram onto a 2D surface, so whenever you are projecting your 3D function onto a two-dimensional surface, especially the convex loss function, you might observe contours like this. So these are level curves or contours where the minima point is somewhere here. So all you try to do here is to find these right values of W and B, the right value of W and B, where you are observing minimal loss. The loss at this particular point is minima. So you just imagine that this is a 3D surface where the minima point is nothing but the valley point. So this is the valley point. And this here is going to be the value that we should be looking for. The corresponding weight and bias values are the right or optimal parameter values that we need to freeze. So this is the overall essence of the gradient descent algorithm. However, I would like to detail out the steps that are involved in gradient descent algorithm so that we are well versed with it. Later, we'll also see what are the different variants of gradient descent algorithm that are existing. The very first step is to do a random initialization for bias and weights. So we are supposed to do a random initialization. Even if you think about initialization that we have done for the weights and biases during our implementation session, we essentially have drawn all these values for weights and bias from a given standard normal distribution by making use of torch.random function. So we made use of this function in order to derive or draw samples of values from a given standard normal distribution. So this is a pretty decent weight initialization technique, especially when you are having a simple dataset. But we need to use good initialization techniques like Hay initialization or Xavier-Glorot initialization, especially to avoid problems like vanishing and exploding gradients. So whatever initialization to the weights that you are doing, it should not result in a smaller gradients or larger gradients. Let's say that the gradient value or derivative of loss with respect to a particular weight value within your network, if it's resulting in a very small value like 0.001 and your weight update for W111 is going to be the current weight value minus eta times derivative of loss with respect to that particular model parameter here. Since your eta value is already very low, like 10 to the power of minus 3 multiplied by 0.001, it's going to result in a very small or negligible value. Essentially, you're not updating your weight at all. If at all you are looking at your initial layers of the neural network, in case of a multi-layer perceptron, if all of these are your inputs and there are weights associated with each one of these inputs for this particular hidden layer 1, then obviously if you are not having any updates to all of these weights, if you're not updating any of these weights, since there are very small values that are resulted for your gradients, then you are not learning anything about fundamental aspects of X. The initial hidden layer generally learns about the fundamental aspects of your X data. Okay. So the later layers of your MLP architecture basically learns complex features. So initial layer always learns about the fundamental features of your X data. So if at all you're not updating your weights at all, you're not learning anything. In such cases, you're not learning the fundamental aspects of X itself. Then forget about the complex features that you might derive in your subsequent layers. So it's always very critical for us to do a proper weight initialization, to implement a proper weight initialization depending on the data that we are having. Okay. And then the second step involves the forward pass, which we clearly know. So in our implementation, we had one neuron and multiple inputs and one output here. The activation function that we have used was a linear activation function where f of z is going to be z itself. Z here is summation of I equal to 1 to j wi xi plus b. So every single input that's being connected to this particular neuron from its preceding layer had a weight associated. We have an additional bias associated with this particular neuron as well, which is given by this particular weighted sum of inputs as well as the bias here. So this is your predicted y value, which is z. F of z is going to be z itself since it's a linear activation function. So once forward pass is completed, you compute the loss, which is expressed in terms of w and b parameters, which is nothing but the MSE value here. So once the loss is computed, you are going to update your weights and bias by the weight update equation that I provided to you earlier. So this is a weight update equation that we have clearly spoken about in the previous session as well. So at a given point, let's pictorially represent this in the form of a 2D for now. If this is your randomly initialized weight, and now you compute the gradient at this particular point, which is given by dou j by dou w or dou j by dou w. This is a partial differentiation since there are multiple model parameters involved here. Once we compute the gradient, now you basically subtract eta times that gradient from the existing given weight so as to compute the new weight. The new weight could be this. And you recompute your gradient again at that particular point. So the step 5 is to repeat 2 to 4. So we are going to repeat step 2 to 4. So this is an iterative process like I have already mentioned to you, that we generally compute the gradients at every updated weight point and then try to understand if convergence is attained or not. If convergence is not attained, you actually calculate the new updated weight again and then repeat the process till you observe convergence. So convergence is a specific point where you might not observe any much change in the weight value, or the gradient or slope that's computed at this particular point is near zero, or whatever weights that you must have computed clearly decreases and then increase. If it increases again in the next iteration, you stop the process. So whatever convergence criteria that I have specified to you, all of them are valid. Either the weights that are currently decreasing till a particular point and then it starts increasing, then stop the iterative process. Or the slope at this particular point, if it's near zero, stop the iterative process. Or again, if the previous weight value that you have computed and the current weight value that you have computed, they are mostly the same or very similar to each other or negligibly small, the difference is negligibly small, then you stop the process there itself. Then it is said that you have attained this convergence. So here the x-axis is going to be w, y-axis is going to be, or the other axis is going to be b here. This is a cost function. The function that you are observing, the 3D image that you are observing is a cost function, which is generally expressed in terms of weights and biases here. Okay. I believe that you have understood pretty well about gradient descent algorithm and the different steps involved in the process. So there are variants to gradient descent process. I did discuss about the problem of getting stuck at local minima in case of having a different convex function. Let's say that this is your loss function. Your loss function basically is having multiple minima points. And if you choose your random value for your weight to be somewhere here, and obviously in your optimization process, you might come to this particular point. Since the slope is probably zero, then you might stop the process here. You might stop the gradient descent process here itself, stating that we have attained the minima. But this is a local minima. If you clearly observe, we have this particular global minima, which is what we are supposed to attain. So we are supposed to find that particular value of w, where we are observing global minima, not the local minima. The problem of getting stuck at local minima can be solved by approaches like stochastic gradient descent and mini-batch gradient descent. So these are two different variants associated with the gradient descent algorithm itself. So batch gradient descent is nothing but the gradient descent process that we already have discussed. Nothing but the same. Essentially in your neural network architecture, right? So let's say that this is your hidden layer 1, hidden layer 2, and this is your output layer. We have the input layer as well. When you are presenting all your data points, let's say that there are 100 different data points that are available within your data set, 100 different data points and 4 columns or 3 variables to be more precise. Okay. So now all 100 samples are shown to this particular network and your gradients are computed by considering all of these points. Your weights and biases are updated by considering all of these points at once. This is your generic gradient descent process, which is nothing but the batch gradient descent process that we have learned. So when you expose all of these points and conduct a forward pass and a backward pass, it means that you have completed one epoch. So completing one epoch is equivalent to showing all the data points to the particular network and completing the forward pass and backward pass. So when you show all the points and all the points are utilized to compute the all the points are utilized to update the weights and biases, then it is said that we have completed one epoch. So how is epoch different from an iteration? So that's what we are going to discuss now. So stochastic gradient descent is when you're only showing one sample to the network. You only are showing one sample to the network at a time. So to this particular network, you're only showing one particular sample at a time. So you are computing your gradients based on one sample itself. Since there are 100 different observations within your data for 3 different variables, now in order to complete one epoch, you need to complete 100 iterations. 100 forward and backward passes is what you are supposed to complete, since you're only showing one particular sample for every forward pass and backward pass. So in order to complete one epoch, in order to show your complete sample set to your network, you need to complete 100 iterations. So each iteration is a combination of forward pass and backward pass. Essentially, your weight and bias update. In every iteration, your weights and biases are updated by computing the gradients. So now the gradients are computed based on only one single observation that you are showing to the network. So whatever gradients that you are computing are reliant only on one single data point. So the weight and bias updates are very noisy, right? Whereas the batch gradient descent, the weight and bias updates are not that noisy, since you are considering all of these data points in order to compute or average out the gradient that you have. It's pretty smooth. So the weight updates is pretty smooth in case of batch gradient descent. In case of mini batch gradient descent, instead of showing one sample like you have shown in SGD process, you might show a specific batch size samples. Like let's say my batch has got, or my mini batch has got 10 different samples associated. So for every iteration, now I'll have 10 different samples that are being shown to the network. So in total, for one epoch to be completed, I'll have 10 iterations. So that is 10 forward pass and backward pass that are to be conducted. Okay. So how did I arrive at this particular 10 iterations? The total number of samples divided by the batch size. The batch size here is going to be 10. So there will be 10 different iterations in total that are to be conducted in case of mini batch gradient descent, where your batch size is going to be 10. So that's the primary difference between batch gradient descent, mini batch gradient descent, and stochastic gradient descent. As I have mentioned to you earlier, the weight and bias updates are very noisy, extremely noisy in case of stochastic gradient descent, because of consideration of only one single data point in order to compute your gradient. At one particular iteration, your gradient might be very large. The other iteration, it might not be that large. It might be very small. You never know. Totally depends on one single sample that you are showing to the network. And hence, if you are looking at these oscillations are due to the noisy updates to the weights and biases that you have done. Whereas if you look at the mini batch gradient descent, the noisy updates are little less prevalent because you are considering good number of samples in every single batch that you are showing to the network, or in every single iteration that you are conducting, you're showing good number of samples to the network. In batch gradient descent, it's pretty smooth because you're showing all the data. Likewise, you can conduct n number of epochs. So one epoch in case of mini batch gradient descent where your batch size was 10, you have conducted 10 iterations. Likewise, you can conduct like 1000 different epochs, but there is some stopping criteria which we'll discuss later. However, I'm just mentioning a point that you can continue having multiple epochs, and within every epoch you can have multiple iterations as such for doing your weight and bias updates here. In this particular case, you are not stuck at this particular local minima that we have discussed. So in this particular convex function that we have looked at, where this was your local minima, now you'll no longer be stuck at this particular local minima because you are doing noisy updates to your weights and they are not as smooth as what we are observing in batch gradient descent. So these noisy updates to the weights and biases generally escape these local minimas, but there is a good chance that it will escape the global minima as well. And that's when we need to implement certain extensions that we have for these different optimizers. So an extension to SGD where you might actually solve this particular problem of escaping the local and global minima as well by considering these optimizers like ADAM, ADAGRAD, RMS prop, as well as momentum. So all of these or most of these particular optimizers are extensions of SGD process where we consider decaying the learning rate or we are considering adaptive learning rate. So initial updates will have larger values for your gradients, and your later updates are not having that large weight updates. Let's say that this is your convex function, a perfect convex function. This is your initial gradient. You must have computed your gradient value to be 0.121 or whatever it is. In your subsequent update, you are now accounting or considering the previous gradient as well in order to determine what could be your eta value. Your learning rate is not constant in this case. You are adaptively changing the learning rate based on your previous gradients. Okay, you are going to decay your learning rate. You're taking smaller and smaller steps as we progress through this particular minima point. And in conjunction with SGD, since it's anyways doing noisy updates, it might escape local minima, but it might converge at global minima. All of this is your experimentation that we'll have to do when we are presented with a problem. Okay, but I believe you got a gist and fair understanding on what gradient descent is, what are the different steps involved in gradient descent, and what are the variants of gradient descent problem. We have batch gradient descent, which is nothing but the gradient descent algorithm by itself, mini batch gradient descent, and stochastic gradient descent as well. Okay, so that's pretty much all I wanted to discuss with you in this session, and see you in the next session.